Today we are going to discuss the vibrations of rectangular plates. So, in the last lecture we had seen the mathematical modeling of plate vibrations under small transverse displacements. So, today we are going to look at the vibrations of rectangular plates. So, let us recall that the equation of motion for a Kirchhoff plate So, this is the Kirchhoff plate model, where this nabla 4 is the square of the Laplacian, and that turns out to be in this form, and D is in terms of the Young's modulus E, thickness cube, thickness of the plate H cube divided by nu is the Poisson ratio. So, here of course, rho is the density of the material of the plate. So, this is the Kirchhoff plate model for a plate with constant thickness. Now, along with this we will have of course, the boundary conditions which we will look at as we proceed. So, we are interested in the modal analysis . So, we will be looking for solutions we are looking for solutions for rectangular plates. So, this is in the Cartesian coordinates. So, we look for separable solutions, space time separable in this form. So, suppose we have a plate lying in the x y lying on the x y plane, and the displacement, the field variable w, is measured in the transverse to this plane, which means perpendicular to the plane of the paper. So, if you substitute this solution form in the equation of motion, so we can write this as and we will make a redefinition of. So, we will rewrite this as where we have defined this gamma as omega square rho times the thickness divided by this constant d. So, this is our differential equation of the eigenvalue problem. So, the complete eigenvalue problem description will also have the boundary conditions along with this differential equation. So, let us look at this differential equation first. So, we have, I can write this as this operator in the equation of motion. So, I can write this as nabla power 4 minus gamma power 4 operating on W, and that is 0. And I can factorize this in this form. Now, these two operators, they commute. So, this can operate first or this can operate first, it does not matter in which order. So, then if I consider two functions such that this operator operating on W1 is 0 and W2 is such that so these two functions satisfy these differential equations. Then I can say that the solution W can be written as a combination of W1 and W2. So, this can be very easily checked, that you can if you construct a solution like this, then this is going to satisfy our original differential equation of the eigenvalue problem. Now, but this it so happens, this is as we will discover very soon, that this is not the most general solution or structure that is possible. So, this solution is valid or good for a class of problems. So, class of problems, by class of problems I would I mean that class of boundary conditions. So, this structure can be used to satisfy a class of boundary conditions. Now, then let us look at let us search for solutions of this class. Then we have to look one by one at these two differential equations. So, let us first take this differential equation, which this differential equation. Now, this differential equation is also known as the Helmholtz equation, which we have come across in the when we discussed dynamics of membranes. So, when we studied the eigenvalue problem for membranes, then we have encountered this differential equation, and the solution we can recall is in this form. So, the general solution of this differential equation is so that is the general solution of the Helmholtz equation. Now, where this alpha and beta they satisfy the condition that alpha square plus beta square must be equal to this gamma square. So, this we have already discussed. Now, let us look at the other differential equation. So, this lambda square, the Laplacian minus gamma square so operating on W2 is 0. So, then let us look for solutions with the structure which are separable in x and y. So, if you substitute this solution form here, then I can write so let me indicate this by dots. So, what I have used is this is del x or ddx and dot indicates ddy. So, if I divide this equation throughout by x y, then so I have this structure of the equation. Now, you see that this term is solely a function of x, this term is only a function of y, and this is a constant. So, for arbitrary x y, if this equation has to be satisfied, then each of them must be constants. So, that would imply let me indicate this constant by alpha bar square. So, and y this constant by beta bar square. So, in that case what I have is alpha bar square plus beta bar square must be gamma square. So, now let us look at these differential equations for capital X and capital Y. So, these differential equations they read so double derivative of capital X minus alpha bar square x must be 0, and we know that the solution of this differential equation may be written as so let me write this as the first term as a sine hyperbolic similarly from the second equation so the solution of this can be written as C 3 sine hyperbolic beta bar y plus C 4 cos hyperbolic beta bar y, and of course, this with the condition that alpha bar square plus beta bar square is equal to gamma square. Now, then let me write down the solution so far. So, our W is W 1 plus W 2, therefore, we have all these terms Now, you see, so the actual solution of this W 2, so W 2 is x multiplied by y. So, now this product I can write, therefore, product of say C 1 C 3 if I write as A 5, then so this is A 5 sin hyperbolic alpha bar into sin hyperbolic beta bar y. So, then I can so now you can see here that we have product of the trigonometric functions in x y direction and product of the hyperbolic functions separately again in x y directions. In this class of solutions, there is no product of trigonometric and the hyperbolic functions. So, so this solution we can, I mean, we can intuitively have an idea that this is not general enough. So, but this solution, this is nevertheless a solution which can solve a class of problems. So, this you can use this solution for a class of boundary conditions. So, let us look at certain examples. So, so the first example that we are going to take is that of a simply supported So, let us consider a plate which is simply supported on all four boundaries. So, let us consider this as A and this as B. So, the boundary conditions for this plate we have seen discussed this in the last lecture. So, the boundary conditions so at x equal to 0, which means this edge, and x equal to a means this edge, we have the displacement as 0, and since they are simply supported, So, the moments are also 0, and the moments in this case happen to be the double derivative of w with respect to x. Similarly, at these two edges, the displacement at y equal to 0 and y is equal to b. So, these two edges, the displacement is again 0 and the bending moments are also 0. So, these are the boundary conditions for the simply supported plate. Now, the corresponding boundary conditions of the eigenvalue problem so they can be easily determined from here. So, w So, these are the corresponding boundary conditions for the eigenvalue problem. Now, let us look at the solution and these boundary conditions. So, this so this was our general solution and these are our boundary conditions. So, suppose when x equals 0, so these terms will vanish. So, we are left with these 4 terms. Similarly, when you take double derivative with respect to x and look at x equal to 0. So, again you will find that those terms will vanish. Similarly, when you consider y equal to 0, the displacement and the curvature. So, double derivative with respect to y. So, if you look at all these conditions that you obtain, then finally, using these conditions you will come to the conclusion that this the solution will boil down to now. Here we have used the conditions for x equal to 0, the displacement and the double derivative of the displacement, and again y equal to 0, the displacement and the double derivative of the displacement. So, we have some further boundary conditions which we must satisfy with this equation. So, then if you use those conditions, then so the remaining boundary conditions. So, if you use the remaining boundary conditions, then you will obtain these conditions. So, for example, when you use w at x equal to a equals 0. So, sine of alpha a for all y must be 0, and when you take the double derivative with respect to x, again you will get sine of alpha a equal to 0. So, then you have this condition and you have another condition, similarly sine beta y beta b must be equal to 0. So, this is for w at y equal to b and w double dot at y equal to b vanishing. So, that will give us this condition. So, this implies, the first condition implies that alpha now this gets indexed because there are countably infinitely many solutions of this equation. So, alpha m times a must be equal to m pi, and from here another index so m and n can have values from 1 to infinity. So, if you recall the definition of this, so the condition or the constraint on these alpha and beta that must be equal to gamma square, and if you look back, then this gamma square so so you have this gamma was defined as so this gamma had this omega square. Now, this gamma also gets indexed because of this m and n. So, then omega also gets indexed as m and n. So, omega m n if I now use these expressions of alpha m and beta n. So, this is m pi over a and so that is what we are going to obtain as so this is so omega m n square is given by this. Now, so we obtain the circular natural frequencies of the plate, and using the eigenfunctions are obtained from here. They also get indexed. So, these are the eigenfunctions. Now, you can quickly see that these eigenfunctions satisfy the orthogonality conditions. So, that is A b over 4 . These are the Kronecker delta functions. So, they take the value 1 when the two indices are equal. So, these eigen functions, they are orthogonal, and the general solution we can write down the general solution of for the plate using these eigenfunctions where I have converted this to an amplitude and phase form, the temporal function. So, we can have this general solution. Now, let us look once again at these eigenfunctions. So, these are we have obtained these eigenfunctions even for membranes, and so the modes look very so the modes of vibration are the same. So, for the simply supported plate and that of the membrane. Now, let us look at another example of the plate with mixed kind of support. So, on two edges we consider simply supported edges, and the other two opposite edges we will consider as clamped. So, let us consider this membrane, this plate. So, in the x direction the length is a and here it is b again. Now, we will assume that this side is simply supported and these two sides are clamped. So, these two are clamped and these two edges are simply supported. So, the boundary conditions for such a plate with such boundary conditions. So, the mathematical representations are the displacement at x equal to 0 and x equal to a, they must be 0. The moment these also must be 0 at the simply supported edges. For the clamped edges, we have the displacement at y equal to 0 and b as 0 and we have the slopes at at these two edges as 0. So, corresponding to these boundary conditions, the boundary condition for the eigenvalue problem now, if you look at these boundary conditions and also look at, so these are our boundary conditions now and the kind of solution that we had here. So, if you now use these boundary conditions for this solution, then you will find that this solution cannot satisfy this set of boundary conditions. That can be checked. You have here at y equal to 0 and once with single derivative of y. So, because of this structure being a little special, these boundary conditions cannot be satisfied by this class of solutions. Now, so we have to start afresh for this boundary condition, this set of boundary conditions. We have to look at the eigenvalue problem afresh. So, let us look at so this was the differential equation of the eigenvalue problem. Now, here we have simply supported edges at x equal to 0 and x equal to a. So, let us try a solution which already satisfies this boundary condition, these two boundary conditions. At x equal to 0 and a, the displacement and the moments being 0. So, and we know this, that sine m pi x over a is a function which satisfies these two boundary these 4 boundary conditions, 2 on each edge. For the y coordinate, let us have this function, unknown function, as yet unknown, capital Y, which is a function of the y coordinate. Let us try this solution in our in the differential equation of our eigenvalue problem. So, if you substitute this in here and make some simplifications, then so this is what you are going to get. Now, we can try a solution for this. Let us say, so if you try a solution like this, then P will have as you can see that this differential equation. So, this will reduce to this can be decomposed as so that implies that must be 0. So, we have two solutions of P. Let me call them as so let me name these solutions of P as, let us say, alpha. So, P1 is alpha equals, so let me consider this, so gamma square plus and P2 I will call that as beta So, we have these two solutions, and so correspondingly we can write y as so if you define this beta in this form and alpha in this form, then I can write the solution So, because of this definition of beta, which is so the you have both real and imaginary solutions of for p, and by defining p 2 in this form, I can write this in terms of trigonometric functions. So, then my solution stands as now we have satisfied 4 boundary conditions by choosing the function in x. We are left with these 4 boundary conditions as yet. Now, if you substitute in this solution form in these boundary conditions, finally you will get the characteristic equation So, for non-trivial solutions of C 1, C 2, C 3, C 4, so this is our characteristic equation. So, if you solve this equation numerically, and you already have the relation between gamma and the frequencies. So, you can find out the natural frequencies. Now, this so, I have written out the first 3 modes, and if you look at this this definition, so this is also square. So, gamma is gamma power 4 is so from here you can determine the natural frequencies. Now, this figure shows the first 3 modes of vibration of this plate, So, in the first mode there are no nodal lines, whereas the second and the third modes they have these nodal lines. Now, here you can see these two are the clamped edges. So, the slopes are 0, whereas these are simply supported edges. So, to recapitulate, we have today discussed the vibrations of rectangular plates, and we have seen that the solution is determining the solution is little complex. We have looked at two kinds of boundary conditions or two classes of boundary conditions, and we have solved these problems and determined the eigen frequencies and the modes of vibration. With that, I conclude this lecture.